All right, it says 4:15 on my clock, so welcome everyone to this week's colloquium. It's my pleasure to introduce our speaker for this week, Professor Antoine Browaeys. I think I first met Antoine some years ago in Brussels, if I'm not mistaken, and the one distinct memory that I have is really, and I say this quite honestly, being absolutely floored by his presentation at the time. It really combined, new and exciting experimental techniques with deep physical intuition on a specific problem that I had already been thinking about myself quite a bit. And so I'm really delighted that Antoine can join us today for this colloquium, especially given that it's already past 1 a.m. in Paris, where he is. As a bit of background, Antoine studied at the École Normale Supérieure in Cachan and did his PhD under Alain Aspect at the Institut d'Optique on the cooling and magnetic trapping of metastable helium, which then led to the first Bose-Einstein condensation of this element. He then spent 2 years at NIST in the laser cooling group led by Bill Phillips, after which he was hired as a scientist at CNRS in 2003 in the group of Philippe Grangier. Since 2010, he's been leading his own group at the Institut d'Optique, where they've been working on experiments manipulating individual pole atoms as well as small, dense atomic clouds. By controlling the interactions between these atoms in these systems, he explores a multitude of different topics, ranging from quantum magnetism and synthetic topological matter to different ways that scattering of near resonant light can be used in quantum technologies. Just as a quick note, if you have questions during the talk, please write them down in the chat and send them. We'll be able to see them. And Antoine has kindly worked in a sort of natural stopping point halfway in his talk. So I'll try to take some questions that are kind of relevant to the first half of his talk at that time, and then we'll save the rest of the questions for the end. Welcome virtually to Berkeley, Antoine, and please take it away.
Thank you very much, Norm. This is very nice of you, this introduction. So I hope I will stay clear until the end of the talk. It's true, it's a bit demanding. It's late in the night here. What I would like to discuss are experiments that we have been doing in our group over the past few years. So our group, technically speaking, is not in Paris, despite the Eiffel Tower here. It's at the Institut d'Optique, which is located 20 kilometers south of Paris. So it's actually on a campus, which is called the campus Université Paris-Saclay. So it's kind of a new campus, which actually gathers 25% of the research done in France. So this is, it tells you how centralized the country is. Anyway, so the title of the talk is Many-Body Physics with Arrays of Individual Rydberg Atoms and Optical Dipoles, and it covers the two main activities we have in our group. And so before I dive too much into the topics, let me introduce you to the people who do the work. So this is our team. So the picture has been taken pre-COVID. And since then, it has been a bit difficult to have everyone at the same time. So that's the reason why you see people appearing in distinct pictures. But in any case, most of the group of what I'm going to report today has been done by this crowd of people at various times. And very importantly for us, we need to be supported by theorists because when we are traditional AMO physicists, so to speak, so not very well trained in condensed matter physics and many-body problems. And so we have many collaboration with theorists. So I will show you some results we had recently with the group of Andreas Leuchli in Innsbruck. And we are also collaborating very actively with Hans-Peter Büchler in Germany and with Norman Yao, actually, whom you know pretty well. And we also have on the other topic, which is the light scattering problem that I will discuss, a collaboration with Charles Adams, Ivan Hughes, Direct Chong, and Ana Asenro Garcia, who is in Colombia, in New York. Okay, so I guess that I should start with the general framework of what we do. So we try to study many-body physics with synthetic matter. So, I mean, the loose goal of, loosely speaking, the goal of many-body physics is trying to understand the macroscopic properties of ensemble of interacting quantum particles. And of course, said this way, it covers a wide range of situations in physics. I mean, I just placed here a few iconic ones: superfluidity, superconductivity, the study of magnetism. But it's not only condensed matter physics which matters, but you can also go to the universe and look at neutron star, high energy physics. And all this is falls in this category of many-body physics. And obviously, we know a lot about those systems. Physics has developed methods over the last 100 years to understand those systems, but still there are many open questions that we have, and quite often it's as simple as not exactly knowing what is the phase diagram of those systems, so what are the ground state properties. It's also very hard to understand the dynamics of many of these systems when you place them out of equilibrium. And you need to, of course, realize that if you want to do an ab initio calculation of a complicated situation, essentially past a few, like around 40, 50 particles, it's almost impossible to do those calculations. Doesn't mean that we don't do anything about the system, obviously, but still you cannot do over ab initio calculations. And then there are new questions that arise, for example, the role of topology. I mean, this has been going on for quite some time. Of course, the problem of what happens if you place disorder in this system, how are the properties influenced? And there is a question which is also, what is the role of entanglement in this system? And this is kind of funny because if you open a modern textbook in condensed matter physics, you still very rarely see the word entanglement, despite the fact there is a large effort at the research level to try to classify phases of matter based on their entanglement properties. So very clearly, the field of quantum information, so to speak, merges with solid state physics and condensed matter in order to define new ways or defines in new ways the phases of matter. Of course, as we are interested in those open questions, how do you tackle then when you cannot apply the usual theoretical method? And that's the idea that was put forward a very long time ago and has been refined, of course, which is to use all the experimental control that we've gained over artificial quantum systems, which are called synthetic matter, in order to implement the Hamiltonian of interest. The thing which is important is to realize that those Hamiltonian of interest are not necessarily idealization of real life situation. They can be Hamiltonian that theoretical physicists put forward in order, for example, to study particular kind of symmetries, the role of the interactions, the role of the structures. And to a certain extent, those synthetic matter are a bit more tunable than the real life system. If you want to change the interactions between electrons in a metal, this is not so easy. In principle, with atoms or ions or artificial matters, you are allowed to do that. So this is one virtue of this approach, which is named quantum simulation, but it's actually more general than that. So when we think about many-body physics and many-body system, quite often what comes first to our mind are spin models. They are the first one that we encountered in traditional statistical mechanics textbook, for example. And just to make it even simpler, we're going to consider an ensemble of interacting spin 1/2 particles. So we're going to pin them on a lattice so they don't even move. We only consider the spin degrees of freedom. And people have written different kind of Hamiltonians that I will use extensively during this talk to describe various situations. So there is first the Ising situation, which is an Hamiltonian of the form sigma z, sigma z. So the sigma z has the usual Pauli matrices describing spin 1/2 system. And so essentially what this Hamiltonian tells you is that if the two spins have the same direction, then so either up or down, then their energy is opposite to the case where they are one up, the other one down. The second type of, so this is just a diagonal shift, if you wish, that you consider in the spin basis. So now you can write other kind of Hamiltonians, and another extreme case is what is called the XY model. It has different names actually in the literature, but this is what is called a flip-flop interaction. So that's really an interaction that drives the exchange of the spin between the spin states between two particles, I and J. So those Hamiltonians, they are encountered in many different situations. I mean, usually we learn them in the context of magnetism to describe the macroscopic properties of matter, considering the knowledge of the behavior of the spin of the electrons, for example. But you can also find them in other type of situations which are not necessarily related to spin physics. So for example, one example that I like kind of a lot is the study of photosynthesis. So essentially, photons drop energy somewhere in a chloroplast, in a light harvested device, and the energy which is dropped by the photon has to be moved and carried away to a place where a chemical reaction takes place. And actually, it turned out that people who model this kind of thing use this kind of exchange Hamiltonian here to describe the propagation of energies in this system. Another example, but it will be clear in the second part of the talk, is if you study light scattering in an ensemble, it's exactly can be governed by this kind of Hamiltonians. The conductive properties, for example, of organic polymers can also be described by this type of system. So in a sense, those spin models, they are generic of a whole class of many-body system, and you can study a genuine quantum phase transition, for example, using them. So of course, people are looking at many different platforms in order to implement spin models. Those platforms belong to either artificial atoms, so it can be quantum dots, quantum circuits. It can be more traditional AMO platforms, molecules, ion, atoms that you place or not in optical lattices. It can be magnetic atoms. It can be photons interacting with atoms. So there is a whole class of those synthetic matter where we try to have as much control as we can over them. So the systems that we have at the Institute Optique, we've developed over actually many years, are twofold, and I will try to cover the two of them. First, there are arrays of individual atoms that we can excite to Rydberg state. So these are examples of pattern. I will describe a bit more in a minute, but essentially each dot is a single atom separated by from its neighbor by a distance of typically 10 micrometers. And the second system that we have is a system where we have an ensemble of atoms, structured or not structured, where we study what happens if you shine light on this system. So the light polarizes the atoms. The dipoles that are light-induced interact and modifies the way light is scattered. So the thing which is important is to realize that the length scale we are talking about are different. In one case, it will be the wavelength of the light. In the other case, it's the natural distance between atoms in these arrays. And so each of these systems will implement different class of Hamiltonians. And what I will focus on is the array of tweezers where we will implement the Ising Hamiltonian, and the XY model, the light-induced interaction system, where we will study this exchange interaction. Okay, so those are essentially what I would like to cover. So first, magnetism, simulation of magnetism, if you wish, so exploring the quantumizing model with Rydberg arrays. And in the second part, I will try to show you the kind of activity we have around studying collective light scattering with the resonant dipole-dipole interaction, and show an elementary example of a small atomic chain and how we can observe subradiance in this system. Okay, so let me start with simulation or the study of quantum magnetism. So we will, I will report work that we've done in collaboration with Andreas Löschli in Innsbruck, together with his student, and which amounts to studying the quantumizing model. So a bit more about the platform first. So when I show you those pictures, I said each of the dots corresponds to one atom. So what are we talking about here exactly? We are talking about what is called an optical tweezer. So this is a light field, a laser beam, which is focused by a large NA lens down to typically a size of the wavelength of the trapping light, so typically 1 micrometer. This results into a trap where the intensity is the largest, where you can trap one and only one atom. So this is things that have been developed actually at the Institut d'Optique by Philippe Granger and our group later on. So the typical trap depth is 1 millikelvin, the typical size is 1 micrometer. And so in order to load those tweezers, and there is a lot of details that I sweep under the rug, but that are not too important, the atoms are loaded from a magneto-optical trap, so a cloud of cold atoms. And at the same time that they are loaded, they fluoresce light at a resonant wavelength that you can collect on a camera, just collecting the fluorescence. And so essentially you look at a pixel of the camera, which tells you if an atom is present or not. So if now you need to have many of those tweezers, the easiest way is to keep a single beam, but make it diffract on a spatial light modulator, which will induce a phase pattern on the spatial wavefront. And then Fourier optics tells us that in the focal plane of the lens, you have the Fourier transform of the phase factor you have imposed. So there, now you can, for any geometry you wish, you can calculate the phase pattern you wish in order to create it. So with this, and once again, I leave a lot of details under the rug, but we can assemble arrays of individual atoms. So now the typical number of, it's not the typical, the largest number we can operate is typically a few hundred. So those images are single shot images of fluorescence of atoms, so that we can arrange either in one dimension. So this is what you have here. So this kind of snaky snake pattern, 2D arrays, either in a square geometry or in triangular geometry. We can also assemble them in a completely random pattern. So this is just an example of such a random pattern, which, of course, you may have recognized as a pixelized version of the Mona Lisa. So that's something that was done during the lockdown, where all museums were closed. So we had to invent our own little museum, so to speak. And so what we can also do is to arrange, it's a bit more demanding, but it can also be done, the atoms in 3 dimensions. So these are examples of fluorescence image of atoms assembled in 3D. You have to be careful here. Instead of being single shot images, these are average over many realizations so that all the traps look filled at the same time. Okay, so first part then, arrays of atoms. In such an array, or such arrays, the typical distance between the atoms are micrometers, so 5 to 10 micrometers. So essentially, atoms do not interact at such a distance. So then you need a second ingredient, and this second ingredient was proposed a while ago, actually, by Misha Lukin and Peter Zoller, almost 20 years ago, is to excite the atom to highly excited state called Rydberg state. So they correspond to state with large principal quantum number. So the classical picture of the atom is then an electron which spirals very far from the nucleus. And this classical picture gives you 2 important properties. The first one is that the electrons hardly radiate. So the lifetime of the state is very long, it's longer than it would be in the lower states. And second, you've got very large dipole matrix element between nearby Rydberg state, which scales like the size of the atom. So just because the plus and minus charges are very far from each other. The consequence of this is that because of this large dipole matrix element, the interactions between the Rydberg atoms will be strong. So as an order of magnitude, if you take 2 Rydberg atoms at a distance of about 10 micrometer and the typical principal quantum number we use, so around 60 or more, then the interaction strength is in the megahertz range. So the consequence of that is that any dynamics driven by the interaction is going to operate on a sub-microsecond. And therefore, you see why this lifetime of 100 microseconds looks like long with respect to the dynamics. And therefore, we can essentially ignore it. Okay, so let me show you how we can use one specific type of interactions between 2 Rydberg atoms, which is the van der Waals interaction, in order to implement the Ising model. So once again, if you just take 2 Rydberg atoms and the 2 of them are placed in the same Rydberg state, they will interact strongly. Strongly means that if you place the 2 of them, once again, in the same NS state, so N is the principal quantum number and L is equal to 0, that's the orbital angular momentum, the doubly excited state will be shifted by an amount which is C6 over R6. And the thing which is very wild, so to speak, is the fact that the C6 coefficient scales like the 11th power of the principal quantum number. And therefore, it makes the interaction switchable. If the atoms are in the ground state, N is around 5, we use rubidium atoms. And if you go to the Rydberg state around 50, then you see that there is an increase in the interaction strength of 100 billion in strength. So that's really a lot. And so now if you want to describe that by an Hamiltonian, the Hamiltonian you would put is the following one. This is an Hamiltonian with the strength of the interactions. It has to be diagonal, and it counts the number of atoms you've placed in the Rydberg state. So it's the product of having excited the first one or the second one. So if those 2 numbers are 1 at the same time, you have a strong shift because the 2 atoms are in the Rydberg state. And if only one is in the Rydberg state, the interaction is actually negligible. So you can ignore it. And this is exactly a type of Ising interaction. And because there is a mapping between the excitation and the sigma z, you can rewrite that in the same way. So now what we need is a way to excite the atoms or to couple the ground and Rydberg state. And this we do with lasers. So we use a combination of 2 lasers. So it's a 2-photon transition, so not resonant with the intermediate state, a blue and a red. We start by preparing the atoms by optical pumping in a well-defined state. And then we go all the way up to a well-defined Rydberg state. And so this interaction for what we will, those laser excitation for what we're going to discuss can be, the details can be ignored, and essentially those are just a down and an up state that are coupled by a Rabi frequency omega. And this interaction is actually coherent, and so you can drive a Rabi oscillation between those two states. So the transition is in the UV, and it's 297, it's broken in those two steps. And you see these Rabi oscillation, which are pretty well contrasted, and which occur over time scale, which are a sub-megahertz. Sorry. So now if we want to write the full Hamiltonian describing an ensemble of atoms driven by the laser and can interact when they are placed in the Rydberg state, you would have three terms. The first term is the drive between the ground and up state. The down and the up state. So essentially, this is a sigma x term in terms of Pauli matrices times the Rabi frequency. It turns out that now if your laser is slightly detuned with respect to the transition, it will count and add in the rotating frame, essentially, a term which is delta times the number of excitation in the Rydberg state. So those two terms are already the equivalent of a transverse and a longitudinal magnetic field in the Ising language. And finally, of course, you've got the spin-spin interaction, which is, as we discussed a minute ago, just the product Ni-Ng. So this is exactly a quantum-like Ising model. And experimentally, what you can do, you can vary the geometry, you can vary the strength of the C6 coefficient by changing the principal quantum number. You can also change the omega. And so now you can explore the regime where the atoms are independent. So essentially C6 is 0 to the regime where they are overwhelmingly dominated by their interaction. Okay, so with that, we're going just to explore in the next 5-6 minutes a particular instance of an experiment we've performed. Actually, Michel Lukin was doing the same kind of experiment. I will give you a few more details in a second. So just consider a square array. And in this square array, arranged as it is, so the gray circles corresponds to atoms in the ground state. And so I will set the parameters of the interaction in such a way that two atoms that are close to each other cannot be excited at the same time, just because they interact too violently. So this is called the blockade condition. It's not too important. So essentially, you make sure that in the Hamiltonian, your C6 over A6, A is the interparticle distance, is on the order of omega. So the exact weight, same weight for the interactions on the transverse behavior. So now, if one atom is excited at a given place, it prevents the excitation of other atoms at a distance which is set by this C6 over R6 equal omega. And so now you can ask yourself, how many of such excitation can I put in the system at zero energy cost if I assume that this is nearest neighbor interaction? Well, then I can come up with this staggered configuration of having an atom in the Rydberg state, the ground, Rydberg, and vice versa, or the opposite configuration, and the two are degenerate. So it looks very much like an antiferromagnetic configuration where you would have an alternance of spin up and spin down. So this is how magnetism comes in this simulation, based on the fact that you have used these blockade conditions. So now things are, of course, a bit more complicated. I mean, you can draw a 2D phase diagram of these spin 1/2 on a square array. And those spin diagrams have been studied in the quantum regime. So when you have both omega and delta, in around starting as early as 1970, and there are still developments going on. So that's the thing which is kind of amazing to me. So the generic feature of the phase diagram is the one which is represented here. So essentially, you've got two phases, a paramagnetic phase where the spin will align along any magnetic field set by the transverse component and the longitudinal component. There is a second order phase transition which separates that, the paramagnetic phase, from the antiferromagnetic phase. And when you are back on the classical line, this is exactly one of the configurations I've described here. So this phase diagram, amazingly enough, until recently, had only been known through quantum Monte Carlo, so essentially numerical methods. There were not any direct implementation in a clear instance in the quantum regime of this model. So as I was mentioning that people are still looking at details of this phase diagram. So now if you release the condition of the nearest neighbor, but you allow like tails of the interaction that you can find, and it was done by Subir Sachdev and his team in Harvard, you can find that there are some new phases that occur close to the boundaries here. Okay, and so you see this phase diagram is still under exploration. Okay, so now if you want to map this phase diagram experimentally, how do you do? So you will use an adiabatic procedure where essentially you vary as a function of time gently so that you do not excite the system too much. The two parameters you've got, the control parameters, so essentially the omega, which is the intensity of the light, and delta, which is the detuning of the laser with respect to the transition. And the hope is to be able to drive the system at any given point, starting from the paramagnetic phase where the atoms were prepared in the ground state. So let's go and show you one example of this. So we just start with a 10 by 10 square array, and we just apply this adiabatic sweep. We choose a particular Rydberg state n equals 75, it's not too important. And then we take a final picture after we've swept the laser parameter. And what we obtain is this kind of figure. So you see that compared to the initial one, every other atom is missing. It turns out, and then you have to believe me, obviously, that any missing atom for us in the detection corresponds to one atom that has been excited to a Rydberg state. So all the atoms that are missing are atoms in Rydberg state. So essentially what we have is exactly this staggered configuration of Rydberg ground, which is this antiferromagnetic Néel state. So this is the demonstration that you can prepare this Néel ordering in this system. Of course, we have to, I have not to lie to you too much, the probability to realize such an exact pattern is at low probability, and because we excite the system, so we have, in many cases, patterns which exhibit a large antiferromagnetic ordering, but where there is one or two defects in the structure. And as I was mentioning, so Misha Lukin explored also this phase diagram, but more the corner of the boundaries I was mentioning earlier. So now we wanted also to benchmark a bit the system against theory, and that's where Andreas Löschli and his team did a lot of work. So we have to define some kind of quantity that you can compare with numerics. And so we've chosen, not too originally, the staggered magnetization, which is the order parameter of the situation. So essentially, where you have this kind of bipartite system, where there is an up array and a down array, so a ground array or Rydberg array that are staggered by one lattice site, essentially you can define the order parameter as the difference between the number of spin-off, the number of excitation in one lattice minus the number of excitation in the other one. That corresponds to the staggered magnetization. And so we measure the staggered magnetization at various points across the phase diagram, and we plotted that as a function of the duration of the pulse. So essentially, the duration here corresponds to stopping at various places. The phase transition here is supposed to occur roughly here, roughly at 4 microseconds. And so what we've done is Andreas and his team compared that to numerics that are already approximate method that were MPS methods, so matrix product states. And they did a calculation taking into account all the imperfections that we had independently measured on the experiment. And they came up with this curve. So essentially, of course, the data are the dots. If we had no imperfection in the system, so a system which implements the ideal system, but you allow for, so you have the exact time sweep. So essentially, there is non-adiabatic excitation. They are included in the simulation. You would have the dotted line. So you do see that we are not, we don't have an ideal situation. But if we give and include the imperfection in the calculation, and you average over different ones with different imperfections, you obtain the black curve, which follows pretty closely what we observe experimentally. So it's telling us two things. First is that the system is not ideal, but we do understand the nature of the imperfections in the system. And one thing which is also striking is that for the theories to get one of these gray curves with an MPS that includes a 10 by 10 array, it takes 10 days on a supercomputer to do the calculation. So of course they did that in parallel on different clusters, but anyway, it gives, and while for us taking the curve is one afternoon essentially. So it already tells you that those machines starts to have a virtue, and actually we've done the experiment all the way up to 200 atoms, which is far beyond any thing that can be done on classical computer. Anyway, so it kind of builds a bit confidence in the platform. And so in a sense, the conclusion of the take-home message of this first part is that this is one of the first implementation of the quantumizing model in 2D. once again, I mean, you validate what people knew by numerics, but still, it's nice to have this. And so people were already able to explore the phase transition. So there are a few work from Michel Lukin and Manuel Andres as well. And what we've done, and I'm not going to discuss that tonight, we've also tried to explore the frustrated geometry. So essentially the triangular geometry tree, where there you have the possibility that in an antiferromagnetic ordering, there is a massive degeneracy because you don't know what is the direction of a third spin when you have imposed the already an antiferromagnetic bound here. And so you want to minimize globally, you cannot minimize locally the energy. So that's also something we've explored, and you can look in the publications about that. We haven't seen any evidence of frustration yet, if this is what you're asking, because it's actually a bit demanding. So I think that I could already stop here in case people have questions about this first part, because before I move to the second one.
Yeah, there are definitely a couple of questions already. And again, for others, please feel free to drop your questions in the chat or the Q&A, and we'll ask them to Antoine. One question is a little bit about the tunability of the platform, Antoine. So one of the questions is, you mentioned mainly antiferromagnetic interactions. Is that the case for both the Ising interaction as well as the XY model? And more generally, can one tune in your system between ferromagnetic and antiferromagnetic? Or can one have like mixed interactions in a system where some bonds are ferromagnetic and some other bonds are antiferromagnetic?
So that's a very good question. So, well, and the answer is can be pretty involved. But if we were using the XY interaction, so it wouldn't be a van der Waals, it would be a C3 over R3. And there is an angular dependence of the interaction. So essentially, you can choose the angle between a quantization axis, which is imposed by your optical pumping scheme, essentially, and the internuclear axis to have, at some places, attractive or repulsive interactions. With the van der Waals interaction, usually the sign is the same over all the array. It can be made positive or negative depending on the principal quantum number you use. Usually for us, it's repulsive for the kind of principal quantum number we use with a low angular momentum, so L equals 0. The thing which is important to realize is that the antiferromagnetic ordering I've showed does not depend on the sign of the interactions. This is just a blockade condition. So essentially, when you have a closed system, it means that instead of having your antiferromagnetic ordering, which would correspond to the lowest possible energy state, it would correspond to the highest possible energy state. But essentially, you've got a kind of, I mean, for a closed system, the notion of ground state doesn't make sense because you choose whatever state you want to pick, either the highest, the one with the highest energy or the one with the lowest energy. So I don't know if this is clear. And if this
I think that was very helpful. Actually, related, there's a second, or the third question is kind of actually related to what you were just talking about. So you mentioned that the probability of getting this particular checkerboard pattern is less than 1%. Mm-hmm. And the question is, do you think about that in terms of some sort of a temperature for the final state? Or is it more natural that given the types of errors that exist in the system, that one can't really think about it as a temperature, but that it's really related to some other imperfections?
Okay, so that's an excellent question. So the zeroth order answer is yes, you can think of it as an effective temperature that encompasses the effect of imperfect preparation, imperfect excitation, failure of adiabaticity, and also the errors in the system. So that's the zeroth order, because now if you try to investigate the statistic of the cluster that you create, the antiferromagnetic cluster, you find out that this is not a thermal distribution. You cannot assign a temperature to it. It doesn't have the properties of a thermal distribution. In particular, if you were trying to extract a temperature, it would be on the order of the nearest neighbor interaction divided by 2, typically, so 0.5 J. But then you would find that if you were plotting on the same graph as the histogram of what we obtained on the experiment, a thermal distribution, you will underrepresent what we observe on the experiment, which is the ground state, the antiferromagnetic ground state. So this is not exactly, it is not a thermal annealer, if you wish, that we are operating.
Sounds good.
Yeah.
One last, perhaps slightly more provocative question. So you emphasize that in Andreas's simulations, they take, I don't know, each run takes, 10 days on a cluster or something like that. Is there some sense in which one can think about your experiments as, realizing a different sort of analog version of quantum advantage compared to kind of the digital stuff that we've heard about in other contexts?
Yeah, that's also an excellent question. I don't know what's smart to say about that, because any experiment that operates a large number of atoms, and you just take any experiment done with optical lattices, people have done experiment with 10,000 atoms, and people cannot reproduce the outcome of the experiment with an ab initio calculation. So I'm not sure people would call it a quantum advantage or analog quantum advantage. If we do, then many people have already observed that.
Sounds good. There's a couple other questions, but let you continue for now, and then we'll ask those at the end.
Okay. So now I will completely change topic, so to speak, but of course it will still be related to spin models. So what we're going to look in the second part is a spin model through the eyes of light scattering and the resonant dipole-dipole interaction. So the problem we are looking at is actually very simple, at least in principle, and this is something we've all seen during our studies. So essentially, we just take a gas of atom. So it can be the atmosphere, so a gas of molecules. You shine light. This light is near resonance, and you ask yourself, okay, what is the light scattered by this ensemble? So essentially, you can think of it either classically by just saying, well, I mean, the light will induce dipoles, and those dipoles may radiate energy, it's not may, will radiate energy at a rate which is gamma. But at the same time, they can also interact if the ensemble is dense enough and if you drive the system close to resonance so that the dipoles are huge. So now, instead of having an scattering by the ensemble, which is a collection of individual scattering, you need to take into account the fact that the entire ensemble is going to collectively scatter light. So now, if you want to understand that from a quantum mechanical point of view, what can you say? Well, you can say that this dipole-dipole interaction is the exact equivalent of having one atom which gets excited, all the others around being in the ground state. And there is a process by which one atom, when this atom decays and can be reabsorbed by a nearby, the photons emitted, which is a virtual photon, can be reabsorbed by a nearby atom. So this exactly implements on a two-level system, the sigma plus, sigma minus type of interactions. And people can calculate based on electromagnetism, and it's a bit involved, but in any case, people can calculate the coupling constant that you have here. So under certain type of approximation that I will not discuss here, you come up with actually the field radiated or the energy between two classical dipoles. That's the beauty of this formula, that this is the same as the one you find in the Jackson textbook, despite the fact it has all the quantum aspect in it. So essentially, you recognize the radiation term, so 1 over r, with the e to the ikr, so the propagation phase, and you also recognize a near field term, which is 1 over kr cubed, which if the atoms are close enough, the dipoles interact in a static way, if you wish. The thing which is important to realize as well is that this Hamiltonian that I've written here is now non-Hermitian. And it has to be non-Hermitian because, of course, there is a counterpart of the dipole-dipole interaction, which is the radiation in free space. So the system can lose energy. So this is what you find in this I and e to the ikr. So once again, this is just one, I mean, there are assumptions under that, but I mean, it can be described as non-Hermitian. So now what does it mean dense? I mean, you see here that the natural strength of the interaction is h bar gamma. So now h bar gamma, or let's say kr, dominates over gamma, the natural line width of the interaction, provided the fact that kr is small enough, and this is to say that r, the interparticle distance, is smaller than lambda over 2 pi. And so in this case, the dipole-dipole interaction dominates over the radiation in free space. So now you can think of your problem in a slightly different way. One atom gets excited, and it has two decay channels. Either it can decay in free space, so this is the usual spontaneous emission, or it can exchange its excitation with a nearby atom. So you see again the same classical picture I was mentioning, but from a quantum point of view. Okay, and so you understand why I was mentioning at the beginning that transport properties could be described by this type of Hamiltonian. So people have investigated, of course, this problem over many years, and I just mentioned a few recent investigations using cold atomic ensembles, where the atoms are essentially frozen in space. So there is, the people have studied that with hot vapors, then cloud of cold atoms, dilute cloud of cold atoms. There are many names associated to that. But so essentially, the problem with all these explorations so far is the fact that they were done with random ensemble. So essentially, the position of the atoms are random. So now, if you just remember that the dipole-dipole interaction has a phase factor here, which corresponds to the propagation from one point to another, under the phase of the field, then it means that if you look at a given place in the cloud at the influence of all the other neighbor atoms, all these phase factors essentially are going to cancel, or at least have interfere, but in an almost destructive way. So now, if you want to reinforce, or at least control the importance of this phase factor, it's a good idea to structure the ensemble in arrays. So let's just take the example of 1D chain, if you wish. You can have two kinds of configuration. I mean, if this dipole-dipole interaction acts between those classical dipoles, you can have a situation where all the dipoles are in phase, in which case all the fields are going to interfere constructively, and therefore you will have a decay of the entire ensemble at a rate which is larger than the rate of individual atoms. So it's called the Subradiance regime. And then you've got the other situation where now you've got an alternance of up and down. So the phase of the field emitted by all, or radiated by all these dipoles, are going to interfere destructively. This is called Subredness. So this is a very classical picture that can be made completely quantum. And actually, that was made quantum in particular by the group of Direct Chang in ICFO a while ago already. So where they predicted the following: if you have an interparticle distance which is less than wavelength of the light, essentially you've got a photonic crystal type of condition, which is that the modes, those Subradiance modes, are going to be guided along the chain. So the only way the system can radiate is through its bottom. So you cancel the possibility that those Subradiance modes radiate transversally to the chain. People have looked at all these, control of the dipole-dipole interaction in order to build better atom-light interfaces, optimize cloud, look at topological situation, try to make that as a nonlinear medium. And there were very few experiments until now, apart from the one that actually Dan participated to in Max Planck, in the group of Emmanuel Bloch, where they realized that on a 2D array, they could show that actually it could reflect the light. And you observe also Subradiance in this system. So that's the first experiment that demonstrates that in a controlled ordered array. Okay, so what we've done is a bit more humble than that. We try to look at what happens if we scatter light along a 1D chain. So that's the first thing I want to show you. So it's all in a classical regime. You can all interpret the experiment that I'm dealing with in the low intensity limit. So essentially, you just take a chain of atoms. How do you do that? You just take a single tweezer, which ensures a transverse confinement of the atoms. And at the same time, you retroreflect the light in such a way that you create an array. Okay, so there is almost a 1D array. The 1D array is not unit field because the atoms essentially have a probability 1/2 to be sitting at one given side, but you got one at most on a given side. And so what we've done is trying to excite this light along two different directions, either with this chain along two different directions, either along the long axis of the chain or transversally. And we always measure the fluorescence emitted at 90 degrees. And you've got the two excitation laser, and you measure in the third direction. Interparticle spacing is on the order of the optical transition of rubidium, so 780, a bit larger. And we can, thanks to the imaging that is a two-axis imaging, so we have a high NA lens both on this axis to create the tweezer, but also to image transversally, we can measure the resonance as we move along the chain. Okay? And so what we have observed is that if we shine the light transversally to the chain, we observe an excitation spectrum, so essentially an amount of light that you collect in fluorescence, which essentially is centered at zero detuning. So this is when you vary the detuning of the light. But if you shine the light along the axis, instead, you do find that there is a shift of the resonant light. And so you can even measure the position of this shift and the magnitude of this shift as you move along the line. So essentially for any of these slices here, spatially, you got such a spectrum, and you can see that as you move along the chain, you observe that the light is, the fluorescence is more and more shifted. Where does it come from? Well, actually, it's classical electromagnetism at the end of the day. So it's just that you've got, at a given place in the chain, the interference with all the field radiated by the atoms located before a given atom. And all these will interfere constructively and result into actually a red shift, because these fields are all in phase if you are, and are also in phase with the laser if you are below the atomic resonance. So in a sense, this is the demonstration of the fact that by structuring your ensemble, you can considerably enhance the optical response, because the magnitude of the shift that you measure in this ordered array is the same as the one we were measuring years ago when we were operating extremely dense ensemble. So they were not structured in 1D, but they were much denser. The interparticle distance was much smaller, and yet we're measuring the same order as what we have with atoms much further away. Okay, so that's one illustration of what I was mentioning. If you structure, you can enhance the optical response. The second thing I mentioned is the possibility to observe subradiance. So subradiance is, idea. The way I've introduced it, this is this idea that you have state with extremely long lifetime. So in a sense, they would be ideal in quantum technology to ensure photon storage. So, and there are many papers which suggest that under various conditions. So always using arrays of atoms, what I will show you will not be done on an array of atoms, but essentially that would be the ultimate goal. So essentially what you need in order to observe subradiance are three things. A medium which is able to sustain subradiance, a way to store a subradiant excitation, and if you want to use it as a storage medium, also a way to release the excitation. So what I will show you in the next, let's say 5-6 minutes is, before I have to conclude, I guess, is the first point. So we have a medium able to sustain subradiance, and second, a way to release the excitation in free space. Okay, so before, I just want to make sure we are all on the same page with what is subradiance here. So just consider again this ensemble of two level atoms coupled with these sigma plus sigma minus type of interactions. We know from our quantum mechanics class that if you got those two level systems that are coupled, you can leave the degeneracy of the two degenerate states, EG and GE, that leads to a plus and minus superposition of the two possible states that are degenerate, EG and GE. And in particular, it can be shown that the symmetric combination has a lifetime which is smaller, which is longer, sorry, so a gamma which is smaller than the lifetime of a single atom, and vice versa. This so-called superradiant superposition, the plus, has a lifetime which is which is smaller than the single atom lifetime. So now this notion can be extended now to a large number of particles, and we build what is called the Dicke ladder. So Dicke, from Robert Dicke, who predicted all this early on. So essentially you classify or you sort the excitation as a function of the number of excited atoms you place in the system. So there would be all the atoms in the ground state, all the atoms excited for this 4 case here, 4 atom case here. You can place 1 excitation, you have 4 states, 6 excitation, and so on. So now, if you switch on the dipole-dipole interaction, so essentially this pairwise coupling, you will, this pairwise conserves the number of excitations, so you diagonalize in each of the manifold. And so what you have now are certain states that have very strong lifetime, and others that are very short lifetime. So essentially, you would have different decay channels through strong superradiant decay or subradiant decay with longer lifetime. So this subradiance has only been measured very recently, actually, in a dilute cold of cold atoms by Robin Kaiser on 2016, so in France, and he was using a dilute cloud. So the atoms were very far from each other, but in order to make the influence of the interactions more important, the cloud was optically thick so that the photons stay a long time inside the medium. We've repeated this experiment. This is what I'm going to show you, but now in a very small cloud. So typically on the size, the size of the cloud is on the order of the wavelength of light, not so much denser, and with many atoms in the system. So things are a bit different. It's not obvious that you could see subradiance as well, because the interaction is not 1/r, but also 1/r cube and so on. So the starting point for us is just now a single tweezer. But in this single tweezer, we do not put a single atom. We have ways to place a few thousand atoms in there. So I don't explain you how we do that, but essentially we can do that. We can take the same kind of tweezer as I was using for the Rydberg, but now we just place many atoms in such a tweezer. So the sample now is very dense with such a small cloud. And so we will shine light on this system. And we, importantly, in order to compare to theory, we will make sure that we're operating with two-level system. And the way we do it is experimentally by imposing a strong magnetic field. If you do that, the Zeeman structure will be split by a lot. And essentially, your laser will only be resonant with one particular transition, namely this closed transition. So this is a very good approximation of a two-level system. So the way we do the experiment is the following. Just take this cloud, which is very dense. You shine the light transversally to the long axis, and you shine very short pulses of light that are very intense. When we do that, the atoms are in free flight. It's a bit of technical details, but essentially we're going to see what happens during the drive. So essentially what you will see here is the fluorescence which is collected on an avalanche photodiode, so which counts the number of photons, if you wish, emitted at 90 degrees, during the 150 seconds during which we excite the cloud, followed by the decay. First, if we operate with a small number of atoms, essentially we have this kind of oscillatory behavior before we switch off the light, which then decays back. And that you can fit with the optical Bloch equations for independent atoms. So essentially, the cloud of atoms for the small number of atoms operate as an ensemble of individual atoms that are not collective. So now if you crank up the number of atoms, what you find out is that the Rabi oscillations are now highly modified with an over oscillation, if you wish, at the beginning. But you also see that things happen when we switch off the light. So I'm just going to focus on what happens after we switch off the light. So this is the driving light, which is switched off. This is the decay for the small number of atoms, and this is the decay for a large number of atoms. So essentially, we do see that the decay is faster at the beginning, so this is subradiance, and become much longer at long time, typically after we've released 10%, 90% of the light, and this is the subradiance. Okay, so we've, showed that it was subradiance. We've just characterized it as a function of the number of atoms, the temperature, and so on. So I'm not going too much into the detail, but just to stick to this idea that it can be used as a storage medium, let's try to think about what is the meaning of this. So this is probably the stupidest way to store a subradiant excitation in the medium, but this is just by waiting. You excite the system. At some point, you stop the excitation, and then you have prepared an incoherent mixture, if you wish, of many kinds of states. Some are superradiant, some are subradiant. You let the system decay because it's not driven any longer. And of course, the fastest decaying states, so the superradiant state, are going to decay first. So you filter in such a way that after some time, the only state that remain are the long-lived ones, so that are the subradiant state. Okay, and so now, so at this place, essentially what remains in the system are subradiant light excitation, which you would like to release from the cloud. How do we do that? Remember that subradiance and any collective effect comes from the fact that you've got an ensemble of atoms that are all coupled by the dipole-dipole interaction, but the interactions has to be made resonant. So all the frequencies of the atom has to be the same for this coupling to act. So now, if you had a way to change the resonant frequency of all the atoms differently from one atom to another, you have now an ensemble of independent emitters that are no longer coupled by the resonant dipole-dipole interaction. And this is exactly the idea that we have operated. If at some point you turn back on the trapping light, the trapping light is going to impose on the atoms a light shift on the internal state of the atoms. But this light shift is going to be different whether the atoms are right at the bottom of the tweezer or slightly on the edge. And as we are operating on a random ensemble, these light shifts are going to be random as well. And in this way, we kill the coupling. And so what we expect as a signal is that after the decay, if we turn back on the trap, we kind of change the resonant frequency, kill the resonant coupling, and we should see some kind of burst of light coming out. So this is a simulation, and if we go to the lab and do the experiment, this is what we obtain. So essentially, you switch off the light, you wait, you got the Subradiant tail after some point, and then you turn back on the trapping light, which is here very pedantically called release beam. And then what you observe is a bunch of light which comes out and which actually comes out. And if we don't have enough time on this particular data, but you would see that the decay now follows the decay of a single atom, which is normal because the atoms are not coupled any longer. So you've killed the subradiance in the system. Okay, so that's all I wanted to show you about subradiance and how we can more or less, at least do a proof of principle demonstration of ideas that people have suggested on how to release a subradiant excitation. And just as an outlook on this second part, we have also obviously explored the counterpart of subradiant, which is supraradiant. We've observed the pulses, and so you can find a bit more details here. Things are less new here in the sense that supraradiance has been much more explored in the past than subradiance. But okay, in any case, in this card, this is a system where you can observe both at the same time. So what is actually the exciting direction we would try to follow here? I mean, what you would really be interesting is not only supraradiance and subradiance, but that's the statistic of the light which is emitted by the cloud. And in particular, you are interested to see whether you can generate non-classical statistics, so some kind of squeeze state, or even more violently, squeeze state, essentially, or anti-bunch light. And so now if you manage in a way, and this is more futuristic, and we have an ongoing project in the group, but we are very far from being able to do this experiment. If you structure your atomic ensemble with a sub-lambda spacing, smaller than lambda/2, then the subradiance excitation should actually behave in a fermionic way. So you should have some actually mapping between those subradiant excitation and a Luttinger liquid. Actually, people have promoted this kind of analogy. So essentially, you would see a fermionization of the subradiant excitation. So it's a bit akin to the Pauli exclusion principle. So there are lots of proposals around. Unfortunately, all of them require that the interparticle spacing is lambda/2, which is a bit challenging experimentally. There are ways to circumvent that, but so far, no one has really demonstrated that. Okay, so that was all I wanted to show you on recent experiment we've done. So I come to the conclusion. So hoping that I convince you that this is kind of a neat platform. You combine arrays of tweezers, arrays of atoms, dipole interaction, and you can do either many-body physics. You can explore quantum optics, an atom-light interface, and in situations that actually clearly challenge theory those days in terms of numerics. We still need the conceptual input of the theorists, of course, but I mean, at least on the numerical methods, it's a challenge. And so with that, I would like to thank you for your attention. So.
Wonderful, super inspiring talk, Antoine. Yeah, a reminder, if you still have questions, there's quite a few already, but if you still have questions, please feel free to drop them in the chat or the Q&A, and I will be happy to relay them to Antoine. Okay, the first question actually goes all the way to one of your early slides. The person writes, it seems from one of your early slides that the lifetime of the Rydberg state increases as you go to larger principal quantum number. Yes. This goes against my intuition that once the splitting of a transition gets large, that the decay rate should also increase. How do I reconcile the two?
Okay, so the thing is that you have, if you remember Fermi's golden rules, that gives you the decay of a state. So you got two parts, d square and omega cube. As you go higher in n, sure, d square increases actually as n to the 4, but the omega decreases as n to the cube, and so the omega cube will go 1 over n, and so you will have a scaling which is decreasing as a function of n. Sorry, we have the gamma, and therefore the lifetime increases.
Yep.
Okay, so you need to take into account two things: the dipoles, but also the narrowing of the state.
Good. The second question asks, in the discussion about the axial, about the fact that there's an axial shift, you'd mentioned that there was sort of constructive interference, but it seemed like the spacing between the atoms was disordered. And so the question is whether or not the disorder in the spacing between the atoms, why should that allow for constructive interference?
Yes, okay. Okay, so that's a very good point, and it's not so easy to explain like this. I will try. Essentially, if you have so it's only specific to a 1D system. It's not specific to being ordered. So if you got a chain of randomly spaced atoms, and if you look at, so it's all a classical electromagnetism argument, and you got the field which drives one system. This field is going to induce a dipole, and this dipole radiates. But if you look at the propagating phase of the field, this is the same as the one that drives the other dipole, because it's a 1D situation. So therefore, they all add constructively. So it's not specific to the fact that it's equally spaced. It's just specific to the fact that this is 1D.
I see.
And as soon as you go away from the axis, the argument doesn't work. And so that's the reason why, if you were sending, and I did not comment too much on that, but the light perpendicular, then the random does matter, because you got a flat wavefront here, but the field radiated by each of the atoms that drive each of the atoms now is random, because it's not imposed by the laser that drives the system. So I don't know if it's clear. I mean, a little drawing would help, but yeah.
Perfect. The next question asks, for the subradiant pulse that you described, is there a natural way to store a qubit in this subradiant pulse?
Well, I don't have a protocol in mind. I mean, of course, people are thinking of it. The only protocol that I've seen so far are about storing photons, but just the energy, if you wish, not storing the quantum state using subradiance. So that I don't know. I don't have any protocol in mind. Most likely, you would have to combine that with some kind of EIT mechanism, so that you can encode two hyperfine state or the polarization state of a photon. But that's the reason I was a bit careful not to call it a quantum memory, because this is certainly not a quantum memory. This is at best, at the moment, a photon storage medium.
Okay, the next question goes back to the first part of your talk. The question asks, in the adiabatic preparation of the checkerboard state, it seems like you took a path that first went up and then through the phase diagram before entering the antiferromagnetic state from above. Is there a reason to do this? Have you tested other adiabatic paths which should have different adiabaticity conditions? And can you see the impact of those, sorry, it's a long question, of those adiabaticity conditions on the density of excitations in your final checkerboard?
Okay, so indeed, we've tried that. So not in a very systematic way, because the experiments are pretty lengthy to study that quite extensively. So the first thing to be said is that as you move along the, let me maybe try to go back to the slide.
Yeah, that would be helpful.
Like, if I can, yes, for example, this one. So essentially, as you move along the critical line, the gap between the ground state and the first excited state vary. So we found out experimentally that actually the trajectories that allowed for the best preparation of the ground state was this one, because the gaps are the highest when you cross from the top of the dome. They close actually and get smaller as you move down. But we indeed tried as well to check some kind of Kibble-Zurek type of mechanism in this system, if this is what you have in mind. And yes, we did check also other type of ramps, so essentially going up and trying to cross here. So we've tried different things. The best results were obtained for the kind of curve that I showed here. So we have a lot of data on this, what you are saying about the kind of excitation we have in the system as a function of various slopes, and we discussed actually recently with Zurek about that, which is Zurek, and so they are looking at our data to see whether we can make a consistent story of that. I mean, this Kibble-Zurek mechanism crossing a quantum phase transition is actually very subtle in 2D to exactly know what is the range of parameters where the mechanism applies. So the only thing I can say is that for certain ramp, we're able to recover from the Kibble-Zurek mechanism the critical exponent that you expect for this, and for other parameters we were not, despite the fact we always add some kind of linear slope in whatever units and whatever scale they need to be. So, but I'm going a bit far. I'm not sure I'm exactly answering the question here, but
I think that,
yeah, so there are a lot of subtleties. Yeah.
I think that touched on all the aspects of that particular question. Okay, one last question. I recognize it's already 2 a.m., but one last question. It's a little bit of a looking forward question from the audience. So you focused on 1D and sort of 2D spin models. And the question is, what are the prospects for sort of really going to 3D and exploring 3D spin models, looking at the physics of things like spin ice in 3D? Is there some sense in which all of the things that you've shown in 2D are kind of already with the current technology naturally doable in 3D? Or where does one go from here?
Okay, so the 3D, I mean, on the paper, yes. There is nothing that prevents it. Actually, we've demonstrated the 3D structure. So now there are some experimental nightmares. The first thing is that if you want to create a real 3D structure, at the moment, the way we do, we prepare those ensembles, or I don't know if you are not familiar with the way we do it, it's not going to tell you too much, but essentially we have to arrange the atoms plane by plane. So the structure has to be arranged in a series of planes, and the arrangement then will take a lot of time. And okay, so you will introduce error. So that's the first thing. Second thing, now you've got a real 3D structure, and you need to laser excite the 3D structure. And so this is, I mean, we're always short of laser power to do this two-photon transition, as everyone is in this field. And therefore, in order to optimize the power, we actually take on elongated laser light so that it's a sheet of light. So now if we want to excite a large 3D structure, this is becoming problematic. So it doesn't mean that we cannot do anything. Like essentially, if we wanted to do a 3D experiment tomorrow, it would be possible, but it would be possible with bilayers. So we could imagine doing a minimalistic 3D structure, which consists of 2 layers of atoms, and already explored this bilayer physics. Going to a real 3D thing with many layers at the moment is very challenging technically. So we need good ideas and also technical improvements. So.
Perfect. Awesome. On that note, let's thank Antoine again.
Thank you very much once again.
For a wonderful talk, and for really patient and staying with us until quite late where you are.
My pleasure.
Awesome. Thanks so much, everyone, for joining for the colloquium, and we will see you next week.
Thank you.
Thanks.
I need to stop sharing.
Yep.
See you, Norm. Thank you very much.
See you, Antoine. See you. Thanks so much. Great to see you. We'll see each other soon.
Sure.
Okay. Sounds good.
Yes.
Bye.